Machine Learning for Absolute Beginners. Chapter 6. Setting up your data. Once your dataset is cleaned, the next step is to split it into two segments for training and testing, known as split validation. This process is crucial for building and evaluating your machine learning models. Typically, the data is divided into a 70 by 30 or 80 by 20 split, meaning 70 to 80% of the rows are used for training, and the remaining 20 to 30% are reserved for testing. However, this is not a hard and fast rule. Larger datasets might benefit from a 90 by 10 split to provide more data for training while still keeping enough data for testing. Randomizing data. Before splitting your data, it's essential to randomize the row order. This helps avoid bias since datasets may be organized alphabetically or sequentially by collection date. Failure to randomize can lead to missing significant variances in the training data, causing unexpected results during testing. Tools like scikit-learn offer built-in commands to shuffle and randomize data easily. Designing your model. After randomizing and splitting the data, you can begin designing your model using the training data. In supervised learning, the model analyzes the relationship between input features X and the final output Y. The model's performance is then measured using various metrics depending on the application, such as area under the curve, AUC, receiver operating characteristic, ROC, confusion matrix, recall and accuracy for classification tasks, or mean absolute error, MEA, and root mean square error, RMSE, for numerical predictions. Using scikit-learn, you can compute the mean absolute error by comparing model predictions with the actual outputs. An accurate model will have a low error rate for both training and test datasets, indicating it has learned the dataset's underlying trends and patterns. If the error rate for test data is much higher than for training data, this may indicate overfitting. Testing and hyperparameters. Once your model can accurately predict test data values, it is ready for real-world application. If the model struggles with test data, ensure that the training and test data were randomized. You may also need to adjust the model's hyperparameters, which control the learning speed and pattern recognition of the algorithm, not the model itself. Cross-validation. Split validation can help develop models using existing data, but it may not remain accurate with new data. If your dataset is too small or the training/test split isn't appropriate, predictions may suffer. Cross-validation offers a solution by maximizing training data availability and testing various combinations. K-fold validation. K-fold validation is a popular method used to improve the accuracy and reliability of machine learning models. Here's how it works. Divide the data. The dataset is split into k equal-sized parts, known as folds. For example, if you choose k equal 5, the data is divided into 5 parts. Training and testing. The model is trained k times. Each time, one of the folds is used as the test set while the remaining folds are used for training. This means that every fold gets a chance to be the test set once. Repeat the process. This process repeats until each fold has been used as a test set. If you have 5 folds, you will train and test the model 5 times, each time with a different fold as the test set. Aggregate results. After all k folds have been used as the test set, the results from each iteration are combined. This gives you a more accurate and stable estimate of how well your model performs. Benefits and drawbacks. Benefits. K-fold validation provides a more comprehensive assessment of the model's performance because it uses all available data for both training and testing. This helps to reduce the risk of overfitting or underfitting. Drawbacks. The method can be slower because the model has to be trained k times, making it computationally more expensive compared to a single train test split. By using K-fold validation, you ensure that the model is tested across different subsets of the data, leading to a more robust and reliable model. Determining data needs. A common question in machine learning is how much data is necessary to train a model. Machine learning works best when the training dataset includes a full range of feature combinations. For example, in a dataset about data scientists, including features like university degree, professional experience, and children, you need a comprehensive dataset that covers all combinations of these features to accurately assess their impact on salary. Why? At a minimum, a basic model should contain 10 times as many data points as the total number of features. For instance, a dataset with 5 features should have at least 50 rows. More features require more data points since combinations grow exponentially with more variables. Generally, the more relevant data available for training, the more accurate the model's predictions. However, there's a diminishing return after reaching a sufficient volume of representative training data. Matching data to algorithms. Choosing the right algorithm depends on the dataset size. Clustering and dimensionality reduction algorithms work well with less than 10,000 samples, while regression analysis and classification algorithms suit datasets with under 100,000 samples. Neural networks require more samples and are ideal for handling vast quantities of data efficiently.